In our class, we've discussed something that is called Newton's second law of motion. And Newton's second law can be summarized in a single equation: acceleration equals the net force divided by the mass. So in these two examples, we got a force diagram of an object with its weight is pulling down on it and its tension is pulling up on it. So we could write this as acceleration equals tension being in the positive direction minus mg over the mass. Now, we could also write it as ma equals t minus mg, or we could add mg to both sides and we'd have ma plus g equals t. Okay, now, is there any profound implication to the fact that I can combine that acceleration plus gravity into the same term? That is the question of general relativity. The force of gravity, the universal law of gravity is g m1 m2 over r squared, and that inertial property, this is not Newton's law. This is, actually, let me put it this way. In Einstein's, what they're saying right here, let me read this part. It says, in Einstein's view, the remarkable coincidence that m sub g and m sub I were exactly equal was evidence for an intimate connection between the two concepts. So let me put that in the equation. We're going to put m sub I right there. We're going to put m sub g there and m sub I there. And then m sub I there, m sub g there. And then we pull that out, and we've got ma plus g equals t. Okay, so this is interesting, and we have pretty much assumed this to be the case throughout the semester, that this mass of the the mass that is affected by the gravitational field and the mass that is due to the inertia is the same. And I think that's a valid thing to say, that mass of inertia and mass of gravity, probably there's no experiment, mechanical or otherwise, that can distinguish between the inertial mass and the mass affected by gravity. However, he then goes on to say that no experiment, mechanical or otherwise, could distinguish between these two cases. Now, that has been carried too far in some situations. People have carried that too far. Now, I am perfectly willing to do this. I am perfectly willing to take tension equals m. Take that out of the equation. Put the a plus g in there. Mathematically, that is fine. There are some people, though, who say you can't tell the difference between acceleration and gravity. If you go to that point where people claim you can't tell the difference between acceleration and gravitational field, I think they're carrying things a bit too far. I think it is perfectly valid to say you can't tell the difference between m sub g and m sub I. Those two quantities are going to be identical. But if you go to the second step and say you can't tell the difference between a gravitational field and an acceleration, that is getting ridiculous. So the two postulates of general relativity are: all the laws of nature have the same form for observers in any frame of reference, accelerated or not. I have problems with that because it is kind of ambiguous. I mean, we can come up with an immediate counterexample to this. Imagine a man standing on a disk that is not rotating, and imagine another man standing on a disk that is rotating. Are the laws of physics the same in the inertial reference frame, where the disk is not rotating, and the non-inertial reference frame, where the disk is rotating? Well, actually, probably not. The man that is on the disk that is rotating is going to feel a force going outward. Well, it's not technically a force. It's technically, it's the centripetal force causing him to, the centripetal force of the friction with the disk that he's standing on, causing him to accelerate inward, but so his acceleration is towards the center. But if the person looks down at the disk, at the center of the disk, then he basically will feel like he's being pulled that way off of the disk, from the center of the disk. But anyway, the physics are not the same in the inertial frame and the non-inertial frame. In one, the man is standing on the disk without any trouble, and the other, the man is being pulled away from the center of the disk. Next, we can imagine a person standing on a bus that's accelerating. For the man that is on the bus that is accelerating, it feels to him like he's being pulled that way, while to the man on the bus that is sitting still, he is not experiencing a force in any direction. So, are all the laws of nature have the same form for observers in any frame of reference, accelerated or not? No. I would say definitely a spinning reference frame is not the same as a stationary reference frame, and an accelerating reference frame is not the same as an inertial reference frame. So the laws of nature, I don't know what that means. It's hard to tell what that means, but just on immediate inspection, we can come up with a couple of obvious counterexamples. So that's not true. Okay, part 2. In the vicinity of any given point, and I think this part is important. You can make this true by making the point small enough, but in the vicinity of any given point, a gravitational field is equivalent to an accelerated frame of reference without a gravitational field. And here's how you can picture this. You have a man standing on the ground, and the gravitational field is 9.8 newtons per kilogram. Or you have a person in a rocket that is accelerating at 9.8 meters per second squared, and he's going to feel what feels like a force downward on himself of 9.8 meters per second squared. So we have just talked about the general theory of relativity, as though it's some amazing thing that Einstein came up with. And the first principle of it was clearly false, and the second one we already know from Newtonian mechanics. So this diagram shows somebody in an elevator, and you don't know whether you've got gravity or some acceleration taking it up, but the suitcase falls either way. And the same thing happens with light, whether it's gravity or Newton's or a force pushing it up, you get the same thing either way. I've kind of taken that. I've got this really. This is a really complicated graph, but I've kind of taken that elevator idea and put it on its side. So basically, the time is going from -1 to 1 here. Space is going in the horizontal direction. So I've got a bunch of numbers doing calculations here. This is supposed to be a photon traveling at the speed of light from the bottom of the spaceship to the top of the spaceship. And this is another photon from the bottom to the top of the spaceship. And you can find out that when it goes from the bottom to the top, you get a smaller amount or a larger amount of time at the detector than you'd get at the emitter, which means you get a redshift going from the bottom to the top. When you go from the top to the bottom, you get a larger amount at the emitter than you did at the detector, which means you get a blue shift when you go from the top to the bottom. And basically the explanation is that the basically the bottom of the elevator is accelerating towards the top of the elevator, and the top of the elevator is accelerating away from the bottom of the elevator. So anyway, you get this blue shift and the red shift, and it basically means that at the top of the elevator, time is going faster than the bottom of the elevator. Now these two things, these two paths are called a Newtonian pair, and it means that basically they're following the equation x equals 1/2 at squared, and x equals 1/2 at squared has this annoying problem that it actually reaches the speed of light in a finite amount of time. If I actually view the Lorentz transformation of this operation from the bottom of the elevator, it looks something really, really weird. So let's look at it, even though it looks really, really weird. So we go from, we're getting closer and closer and closer to the speed of light in a finite amount of time. We reach the speed of light where, boom, and then it starts over, showing the events as they go again. That's fun. Okay, let's look at another demo, because this is the Newtonian pair. And what I've got here is, instead of calling these Newtonian pairs, I'm calling them Bell pairs. Each pair is a Bell pair. It's based on something called Bell's spaceship paradox. And in Bell's spaceship paradox, you've got a whole bunch of you've got basically a bunch of spaceships, all electing to start their engines at exactly the same time themselves, and then come to a stop after a certain period of time. Okay, so you can see here what the plan is. They're all going to, this is what they're doing before they start accelerating. On the blue line, they're all stationary on their marks. At 0, they all begin accelerating, and at 0.95, they all stop accelerating. So that is what everything looks like in the original reference frame. What actually happens, though, is that when they finish, and this is what it looks like when this guy finishes, he sees that all of these guys have already stopped, and they're a little bit further apart than they were originally, because what happened is that this guy started accelerating earlier and finished accelerating earlier, and this guy started accelerating here, finished accelerating here, this guy started accelerating here and finished accelerating there, and they just end up distributing themselves out over the space a little bit more than they were distributed over the space at the beginning, which was much tighter formation. And and that is Bell's spaceship paradox in a nutshell. This last demonstration shows what's called the Rindler pair, and I've got it pretty well elegantly mapped out. So let's see. First of all, let's look at the lines themselves. I don't want the dots in there just now. The whirl lines themselves show basically the front of the rocket, the time at the front of the rocket, and the time at the back of the rocket. And you can see the instantaneous time is marked by these numbers here. Now let's focus on photons moving from the back of the rocket to the front of the rocket. Those photons are redshifted, means that the frequency as they come out of the back of the rocket are less than the frequency as they go into the front of the rocket. Time is going actually a little bit, I think you would say the time is going slower here than it is here. And then we can go in reverse. Let's move the red world lines down and the blue world lines up, the red dots down and the blue lines up, and you can see the opposite is happening. Basically, the front of the rocket is emitting photons received at the bottom of the rocket, and those are getting blue shifted, meaning that the frequency received is greater than the frequency they're sent at. And everything works together pretty much, and so you can see that you can put the dots together and you can see that all of those shapes are preserved. And there's one other thing that I want to look at, is what does this look like? This is what everything looks like from the point of view on the rocket. But what if, instead of being on the rocket, you're watching the rocket from some arbitrary reference frame? Well, what happens to the rocket is, over time, when it accelerates, it does that length contraction that we've been talking about. And when it is traveling to the left, it is Lorentz contracted, and eventually it hits its minimum speed where it reaches its full length. That'll happen right around here, where actually that's marked as 0 and 0 up there. And right now it's going through the negative times. So it'll reach its full length when those both hit 0, and then it'll start accelerating the other way. We got a dog, a neighbor dog. All right, well, I will put these demonstrations in there. So anyway, let's go through the three basic things. There were I talked about the Rindler pair, which is the best description. And then I talked about the Bell pair, which describes a situation where with the Bell pair, there's no Lorentz contraction in the original inertial reference frame, and which means that they are actually getting spread further and further apart in their own reference frame. And with the Newtonian pair, where both of the particles were described with 1/2 at squared, the velocity quickly exceeds the speed of light.